this assignment, you're going to be investigating number systems with different bases. But before we can really talk about different bases, you need to have a very good understanding of a base 10 system. So I'm going to do parts of this investigation from the base 10 perspective, and then we'll look at an example where we change the bases. What digits do we use in our base 10 system? We have a total of 10, and that's why it's referred to as a base 10 system. But the digits are not the numbers 1 through 10, which is a common misconception. The digits start at 0, so we have a way to represent nothing, and go up to 9. And if you count the numbers on this list, there's a total of 10. What are the names of the positions in our system? The names of each of the positions comes from the fact that this is a base 10 system, so I'm going to put a base of 10 in each spot, and then I'm going to put exponents starting at 0 on my power of 10 and working my way up as I move to the left. Because remember, the digit that represents the smallest amount is always in the rightmost position. So 10 to the 0, any number to the 0 power is 1, so we call this the ones place. 10 to the first has a value of 10. So we call this the tens place, and so forth. I know you know this information. I want you to see it laid out this way, so that when we change to a different base, you understand the pattern that we should be following when we have a positional number system, where the order of the numbers and the position they're in matters. I'm going to skip ahead to where you see this written down. You're going to notice the number 3071 with a little tiny 10 at the end of it. This subscript indicates the base that we're working with. Now, normally in everyday life, we don't write that. But because in this investigation, we're going to be looking at bases of 5 or 2 or 6, it is important when you're considering other bases to make it clear which base you're using. So this is just the typical base 10 number that you know and love, 3071. Now I want to take apart that number and show you the powers of 10 that exist within it. So I'm going to create the same kind of chart I did up above. What I want to discuss here is how you represent a number like 3071 as a combination of powers of 10, of the base of this system. I have set up the same kind of chart as above. I've eliminated the middle values section because we have the words here to remind us of that. In this number, how many ones are there? We go to the rightmost position. There's 1. How many tens? We know this position, second from the right, represents tens. So 7 of them. No hundreds and 3000s. If I were to ask you to write this as powers of your base, you would begin here in this column, and notice we said we have 3000s. That's the same as saying I have 3 times 10 to the power of 3. Because remember, 10 to the power of 3 is just 1000. I have 3 times that. To that, I'm going to add, I have no hundreds, is what I've just said there. Now I have 7 in the tens column. 10 to the first is a shortcut way to say 10. So we would write this as 7 times 10 to the first, which you know would be 70. And finally, we have 1 times 10 to the 0. So you'll remember this kind of thing from our skills pretest. Now what's going to happen is when you move out of a base 10 number system, your base can really be any number in the universe you want it to be. So we can have a base of 2 or a base of 3 or a base of 5. And all that's going to happen is we're going to change the bases, but otherwise keep the format the same. So for example, if I was going to explore a base 5 system, it would look like this. It would no longer make sense to call these ones, tens, hundreds. Ones is going to be the name of every first or unit position because anything to the 0 power is 1. But I wouldn't call the second column, which is 5 to the first, tens. 5 to the first equals 5. So believe it or not, this one in the base 5 system would be known as the fives column. And I could continue to modify from there, but I don't want to get too far into that right now. I really just want to make sure you understand the basic mechanics of the base 10 system. So this is how we would expand and write our base 10 number as powers of 10. The next thing I want to explore with you is the operations of addition and subtraction using a model to help us keep track of what we're doing and why. So first we talk about the operation of addition. I'm going to choose two numbers, and we're working in a base 10 system, so remember the digits of the base 10 system are 0, 1, 2, and so forth up to 9. And this is going to be important to remember as we perform our addition. You hopefully do remember the process of addition, where there's some adding and some regrouping. We're going to employ a model similar to what you did in the place value activity from last week. So I'm going to take the number 35 and I'm going to represent it in terms of counters in the tens position and the ones position. But rather than put the digits there, I'm going to put the counters. And that's to help us understand the process of regrouping that we're going to do. So I'm going to put 5 little dots in my ones spot and 3 little dots in my tens spot. I'm going to represent the number 274 the same way, but of course I'm going to need to put in that hundreds spot. Okay, so 274, we now have a hundreds position, and I would put 2 counters there, 7 counters in the tens position, and 4 counters in the ones. So I begin always in the ones place, bringing them all down and together. What I don't want to do is then just count the counters and put the number in that spot. I don't want to try and claim that my answer is this number, okay? It is not. And the problem is, if any of your boxes have multiple digits, that's not okay in a positional number system. You can only have one digit per box. So how do we fix this problem? You do begin on the right, and as long as there's just a single digit to represent the amount, you're fine. So yes, I can put a 9 in this position. Now in the next position, I have 10. Okay, but let's think for a second. I'm going to circle my group of 10 because this is a base 10 number system. That's the same as 100. Each of these dots is technically 10 units for a total of 100 in my circle. So I can take all of these dots, and instead of leaving 10 dots in the tens place, I can transfer them to the box next door. And I can put 1 dot to represent 100. Now I would erase all of these in the loop because I have taken my 10 tens and combined them into 100. Now if I go back to writing my digits, I have nothing in the middle and I have 3 at the end, so we know that the answer is 309, which again, most of you would have gotten. 5 plus 4 is 9, 3 plus 7 is 10. You put down the 0, and remember, we say you carry the 1, right? 1 plus 2 is 3. So this notion of regrouping keeps you within the digits of your number system. Follow along with this example. How would I represent the number 152 in terms of counters? 1 counter in the hundreds, 5 in the tens, and 2 in the ones. 389. Now again, rather than just adding 2 plus 9 and getting 11, I don't want to put the number 11 here because 11 is not a single digit. So instead, I'm going to put my counters in the boxes and then regroup them. Okay, I've combined the 2 dots and 9 dots to create this array of 11. I've combined the 5 dots and the 8 dots to have this combined array of 13, and 1 and 3 to be 4. Now, in terms of knowing what digit to write down, this is a base 10 system. So in any box that has more than 10, I'm going to grab 10 of the dots. This is 10 in the ones position. So each of these dots is 1 unit. This represents a single 10. So I can go over 1 box, I can introduce another 10, and then I can erase all of these. Now notice doing that left behind 1 lonely little guy in this box. So the digit that belongs in this position is 1. Now, When I look at the 10 spot, uh-oh, I've definitely got more than 10 here as well. So I'm going to grab a group of 10, which would look like that. Now each of these are tens because they're in the tens position. So this is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Oh, so everything in this loop represents 100. So I can add a dot here and then erase all of these. Now you'll notice I have 4 dots left behind, and 4 is the digit I'm allowed to use in the system. And finally, when I count the hundreds, fortunately I have less than 10 things here, so I can go straight to the digit 5. This gives us 541. By traditional method, we would say 2 plus 9 is 11. I would put down the 1 and carry a 10 to the next column. 1 plus 5 is 6, plus 8 is 14. Put down the 4, carry the 100. Remember, that's what that is. 1 plus 1 is 2, plus 3 is 5. It's really important that you understand I was grabbing groups of 10 counters because this is a base 10 system. So how does subtraction work then? Well, if you understood the addition and regrouping, kind of moving things to the left as you went, in this case, it's just the opposite of that. So we're going to take and represent each number with counters. Okay. Now, rather than putting together the 2 boxes in the ones column, that was addition, you know, when we are subtracting the lower amount from the top. So in this ones column, we are subtracting 4 counters from 1. And this is where you have to remember being an elementary school kid. You know, if they say, oh, I'm going to take away 4 counters from 1, and the kid's sitting there with 1 penny in their hand, they're like, I can't take away 4. I only have 1. In this case, once again, the problem is solved by looking to the next box over. What you want to remember is that when you have a single dot here in the tens, that represents 1 set of 10 counters. Well, I can move that into the ones position, replace that 110 with 10 individual counters now in the ones position. So I've squeezed in the 10 counters from the 110 that I borrowed the next column over. Well, now you can see I've got a grand total of 11 counters in here. I need to take away 4 of those. And when I perform that subtraction, I could just get rid of this little cluster of 4 in the top left corner, leaving me with 7 counters. So there will be a 7 in this spot. All right, now in the next spot, I have 110, and I'm supposed to take away 3 tens. But you can if you borrow from the next column over. So I circle 1 counter here, and I remember that's a 1 counter in a hundreds spot. That's the same as having how many tens? 100 is 10 tens. So I'm going to represent that with 10 counters. So I can now get rid of this guy because I have moved it into these 10 counters in the tens position. Now can I take away 3? Sure I can. Cross out this one, this one, this one, this one, this one, this one, and that leaves 8. So that 8 belongs in this spot. Now if I have 3 and I'm going to subtract no counters, whew, thank goodness, easy one, it stays a 3. So this is what you're doing when you do this manipulation with the numbers, is you're saying, oh, I have 1, I need to take away 4. Well, I can't. So I look to my next column over and I say, hey, you've got 2 tens. I'm going to borrow 1 of those. So I'm going to lower the count in the tens column to 1, and I'm going to increase the number in this column by 10. 10 plus the 1 that was already there is 11. 11 take away 4 is 7. Same thing happens now when I look and I say, oh, I have 1 counter and I need to take away 3. I can't. Look at the next column over. Hey, you have 4 hundreds. Can I take 1? Sure. So I only have 3 hundreds, and the 100 that I put here adds 10 more tens to the one I already have. So this becomes 11. So if I have 11 take away 3, that leaves behind 8. and 3. And that's the idea of borrowing. I think there's value in showing, not just the algorithm, which unfortunately is what too many kids, that's all they see, and they're confused. Like, why am I lowering this number and what am I doing? Whereas if you let them play with the counters and actually move equivalent things around, it's a much more understandable process. Now, to make sure you really understand the process, you're going to choose a different base and you're going to explore a number system that has fewer digits or maybe more digits.